Hello, guys. Welcome to another episode of CUDA Education. Today, I am going to switch it up on the Apple Metal side. Kind of tired of the regular advanced metal example that we've been working with. That scene has a lot going on with it, but we've been working with that example for a long while now, and just want to switch things up a little bit. And also, it's not just for vain reasons. I think the transparency conversation goes along with our discussion on the depth pyramid, the depth buffer, um, depth value, all of that stuff, right? So this is a natural extension of that discussion, and yeah, we're just moving along, and we're trying to learn stuff and figure things out. So this example is called the order independent transparency example, and if you Google metal sample code and search for transparency, or just click the link down below in the description, it will take you to this example that you could download. It's freely available, provided by Apple. You have to have Xcode. And then you basically, you make sure you have Xcode on your system. You download this example, and then when you try and run it, it's gonna give you a settings error. You basically just have to go into Xcode and say you want to run it locally, right? Sign in locally or run locally or whatever, and that one setting, and then you press the play button, and it will give you this example. All right, so the purpose of this example, this is just my initial run through of the example. Still trying to figure it out fully myself. But basically, this episode is for just an overview of what's going on, and tinkering with what we see. Don't really want to get too involved, as always. Just want to do a quick overview, let it sink in, and we will move into more complexity as need be. But basically, what it is, it's a series of panes that are stacked in front of each other. So there are, several columns of panes that are stacked in front of each other, and the idea is that you know we have these panes that generally you would consider to be transparent, right? Window panes, glass window panes that are transparent. But what happens is that when it comes to computer graphics and your application and actually trying to draw these window panes, um, you have to take into account, obviously, yes, the window panes are transparent, but how does the application, how does Metal process this transparency? So, um, the problem that we're trying to solve here is that if um, you could either just draw the panes randomly, right, and then have the sort of the color, the final color that you see on the first line, have it be determined randomly based on which pane was drawn first. So for example, the green panes aren't necessarily the ones drawn first. Maybe the middle pane was drawn first, then the last pane, then the second to then the second to first pane, and then the first pane, and all of that, right? So the problem is that when you're trying to figure out what is the final color that seeps through all of these panes, right? What is that final color? Right? And you could either do it lazily, where you just say, okay, draw the panes, and whatever pixel, whatever color this pixel resolves to is whatever color it is, right? And it's gonna be an amalgamation of the other panes, but you know sort of the sequence and the order in which you draw it is going to affect what that final color is. Okay, so you could do it that way, which means that you're not going to get a reliable result. You might get, depending on the time of day and the day of the week, and whether it's raining outside, or it's hot, or it's cold, or it's snowing, or whatever, you can't really bet that the final result that you get after processing, the final color that you get after processing all those panes and pixels and stuff is going to be consistent or the same or what have you, right? So, um, instead of doing that, where you just lazily, draw stuff and then you get a final color, whatever it may be, you have a thing of, you have a thing called an order independent approach where, um, you basically draw all the panes, you store all the values of the pixel of that pane in that specific area, and then you do a mathematical calculation to combine those values of the colors of all the panes, and then you come out with a final result that is shown, closest to the camera. Okay. um and this is, it is more expensive on a memory and processing level, but it is also more accurate. Okay, so it is more expensive, but it's also more accurate. um and you got to decide what you want to do, but this is what this order independent and unordered transparency is. So this is order independent, which basically means that no matter what order that you process the panes, you're going to get the same result for the final pixel in the front, because you're not, you don't care what order that the panes were drawn. Okay, you don't care, because you're gonna basically amalgamate, you're gonna summarize, you're gonna summate all of those panes and the colors of those panes at that pixel area, and then you're gonna get a result. So it doesn't really matter what order you draw it, right? So that's what the order independent piece of it means. The unordered portion of it now is when you don't do that process of some, storing and figuring out what the color values are for each pixel of the pane in that specific point in the screen in that area, and you kind of just, you randomly come up with a value based on, what was drawn first, right? So right now we have it ordered, nice and ordered. The application knows all the panes that are there, all the colors, and it says, okay, we're going to mathematically summarize all of these colors, and we're going to come up with a value that is accurate. So we have the order independent piece of it selected right now. When we go to the unordered, we see that we get a lot more chaos, right? Where these things now are dependent on which was drawn first, and it's just sort of, let the chips fall where they may, right? That is my understanding of how this works. And first of all, you could see that on the very closest region of the camera, the very closest pane, you don't have you don't have a consistent color, right? It's all like, depending on whether you're looking here or here or here, it's like all different colors, and like it's just chaotic and random, right? And that's pretty much it. That's my understanding. We're not gonna get into code today. We just want to understand what is it that we're trying to solve here, and what is the problem that all of these things. So we are gonna discuss it some more, and get into more detail, but we won't be touching code. So again, guys, we have the order independent, where everything is done in a rational manner, in a ordered and manner, and we don't care what was drawn first and what wasn't. We generally have a consistent profile for our final, or our closest pane, the first pane, after processing everything below. It's a lot less chaotic, right? And even for like these two panes here and stuff, it's your eyes and your brain can follow logically what's going on with these panes, right? But then when we go back to unordered, we see that we get things a little bit more chaotic, and it's just harder to follow and process. Even like, let's look at this side right here. So yeah, like you could follow what's going on here with this one, right? Even with the panes from the other side. When you go to unordered, it gets chaotic, right? So that's that. Now, let's just stick with ordered for the time being because it's a lot more sane and it's easier for us to follow. So we're going to start rotating the example now, right? So we could see that it's sort of a clean amalgamation of the colors. You could even sort of, mentally follow what's going on, right? It's not too crazy. It's not too you know, it's not too bad, right? But then when we switch to unordered, we're gonna see that things get a little bit more crazier. Okay, let's just process ordered a little bit longer. I really want to look at this one and maybe this one. All right, so we're gonna go to unordered. You guys ready? 1, 2, 3, unordered, and we just get, like, you notice how this one right here, you notice how this one is just pronounced? It's just pronounced. It's like overshadowing all the other panes. Well, I guess even, but I don't know. Right, but you could see here where things are seeping through. Some things have more pronounced than the others, even though they're further back. Maybe it's because it's a heavier color, right? If we go back to ordered, we get things a little bit more sane. Now I don't know if the camera or the application is really taking distance into account when it comes to, because this green right here is pretty solid too, right? So it is pretty solid. So when we go to, like, how come this purple is like overshadowing this green, even though this green is pretty strong and solid, right? So you could see with the unordered and then the ordered that it gets a little bit tricky, right? So that's pretty much what the example is. Maybe this one was drawn first, which is why it has a more pronounced thing. Yeah. Okay. So all right. So let's dive into let's I'll just move it. Okay. Right. Because this one is way back. All right. This one is way back. Um. So let us dive into right. So let us dive into our actual. So this Apple sample is basically a visual demo of why transparency order matters and how different techniques handle it. What the example is showing, in your screenshot, you will see a bunch of semi-transparent colored quads overlapping in 3D space. The key idea: transparent objects need to be blended with what's behind them. But blending is order dependent in the traditional pipeline. So this demo lets you toggle between approaches, right? So we have our order independent and our unordered button to show how the final image changes depending on how the fragments are processed. The core problem: the standard transparency. You must draw objects back to front. If you don't, blending gives wrong results, right? So right, you know, you have to draw these things back, from the farthest object coming to the closest object to the camera. If you don't, blending gives wrong results. Why? Because the blending works like this, right? So this is the equation uh, that is used. That equation is not communicative. Commutative. Order matters. For you guys that are in math class, commutative. This is the perfect example of where you talk about commutative and not commutative equations in math, right? So, we don't just do math in math class for decoration's sake. There's actually real world consequences for these properties in equations. Okay, So unordered transparency, the broken naive case. This is essentially just draw transparent fragments in whatever order they happen to arrive. What happens? GPU rasterizes triangles in arbitrary order. Fragments blend immediately into the frame buffer. So fragments blend immediately into the frame buffer. No sorting. No sorting. Result: colors look incorrect. Overlapping regions appear inconsistent. You might see too much of one color, missing layers, flickering when camera moves. Okay, too much of one color. We definitely saw that. Missing layers, flickering when. This is what your screenshot likely shows. Lots of overlapping quads blending incorrectly because order isn't controlled, right? So order independent transparency, OIT. This is the correct approach without sorting geometry. Instead of blending in immediately, the GPU stores all fragments in per pixel, right? So this is where I talked about the memory cost, because for a particular pixel on the screen, you now have to, remember what are all the other colors that are stacked behind, you know, behind the closest pane for that particular pixel, right? So what are all the other colors? The GPU stores all fragments per pixel, then combines them in a mathematically correct way. So that's where I talked about being mathematically expensive, because now you're taking all of these colors and then you're combining them in a way that you get the color that is mathematically correct for combining all those colors, etc., etc., etc. In this metal sample image blocks approach, each pixel keeps a list of fragments, color plus depth. So we have already played around with the depth. We understand the depth value and what pane is closer to you than the other pane, all of that stuff. After all fragments are collected, they are sorted or composited properly. Then blended in the correct order. Result: correct transparency no matter draw order. So this now relieves you from the constraint of, I drew this pane first over that pane, therefore maybe this pane is going to be more pronounced regardless of the distance or whatever. Correct transparency no matter draw order. Stable visuals, matches what you would get with perfect back to front sorting. So if you were in the unordered world, the only way you could simulate the proper transparency and result is if you made sure that in your unordered world that you drew the panes from back to front, and you had a process to enforce that you only going to draw panes from the farthest to the closest, right? But in unordered world, by definition, you're not necessarily doing that, right? So the key difference is simple terms. So draw order matters, unordered transparency ignored, and order independent transparency ignored. It's also ignored. So in unordered world, it is ignored. In ordered independent, in order independent, it is also ignored, because again, guys, remember, we have a process to make sure that we calculate the proper color. So in both cases, we're ignoring the draw order, for the panes, right? So we're not doing necessarily the farthest pane first and then the closest pane last. We're completely ignoring it in both cases. Visual correctness. Now, the visual correctness for unordered is going to be wrong because we're probably not drawing in the proper order, which means that the color that's resolved for each particular pixel is not reminiscent. It's not reflecting accurately what all those other panes are representing, and the combination of said panes, right? But in the order independent transparency, we do get correct color resolve, because now we are doing we're making sure that we combine. We know what all the colors are. We're combining them in an accurate, mathematical sense, and we're resolving the color to its correct result, right? Uses per pixel storage. This is where I was talking about memory, right? So in unordered world, we're not using per pixel storage. We're just basically splashing stuff on the screen, and we don't care what the pixel we don't care what the pixel is at the end of the day. But in ordered in the order independent world, in the order world, we are storing what the values of these pixels are. So we have to, like the color value. So we have to know, and also the depth value and stuff like that, right? So GPU cost is cheap. On the unordered world, for obvious reasons, we don't have to worry about order. We don't have to worry about draw order. We don't have to store, memorize what the color values are of all the pixels, going down the series of panes, all of that. So GPU cost is cheaper for unordered, and then for ordered, it is for order independent, it is more expensive. Now, I apologize, guys. I apologize. We have unordered and order independent. Okay, unordered, order independent. This is not unordered and ordered. It's unordered and order independent. So I apologize with my language and my words. One thing I've learned in computer graphics is that you really have to be careful with you know how you label things and stuff, because it's a very nuanced thing, and you could communicate the wrong thing if you're not careful. So I apologize. Unordered and order independent. So in unordered world, GPU cost is cheap. In order independent world, it is more expensive because you have to memorize all the pixel values, the color values for each of the panes, and then you also have to memorize the depth values, and then you also have to do the calculation to make sure that the mathematical calculation, when you combine all things considered, you get the correct result. So it is more expensive on the order independent side. Require sorting, no and no. So require sorting, of course, for unordered, it wouldn't require sorting because you're just splashing stuff on the screen. Require sorting. For order independent, I'm surprised it's no, because I don't know. I just thought that would be. I don't know, but it's no. I mean, that's the understanding I have here. Maybe this is an AI hallucination, guys. We're getting our first hallucination, but I don't want to jump out on a limb with that. We'll leave that alone. Why Apple calls it this way: unordered transparency, no guarantees, just blend as fragments arrive. Fragments, guys. We always, generally, for where we are right now, we consider fragments color, right? So whenever you see fragments, you generally think of color. Just blend as colors arrive, right? So no unordered transparency, no guarantees, just blend as colors arrive. Order independent transparency, guaranteed correct regardless of order. I guess that's why sorting doesn't matter here, because you're going to mathematically calculate all of the values anyway, so doesn't really matter. You don't have to sort it because it just knows. So the naming is intentionally contrasting. Unordered, incorrect but simple. Order independent, correct without sorting. Intuition, think of stacking tinted glasses. Unordered transparency, randomly stacking panes equals the wrong color. Order independent transparency, collecting all panes, then stacking them properly, correct color. Right? So that's also another thing. It's like the stacking of them, the distance and the stacking. So, it's randomly stacking the stuff. Why this matters? Sorting transparent geometry is expensive, breaks with intersecting geometry, hard for particles, hair, and foliage. OIT, order independent transparency, solves that by moving the problem into per pixel data structures plus GPU logic. Okay? So it basically takes the burden of calculating these values off of sort of like the physical vector buffers and vertex buffers and stuff like that, and it just does a per pixel thing where it memorizes and knows what all the color values are for each pixel, taking into account each pane, and then it does the GPU logic, which is the math, to make sure that it resolves to the right color after everything is said and done. And that's it, guys. That's it. I don't want to get more deep into this episode, but there you have it. We have our example here, and we are good to go. So thank you guys for watching. Support the channel, guys. You guys know what to do. I don't want to say the phrase again, because like everywhere everyone is saying the phrase. But support the channel. You guys know what to do. All of that good stuff. If you know anyone that's artistically inclined in your community, tell them to get started on this thing. If you you know, if you want to learn, hang out with us and we will learn together. This is Kuda Education. Thank you for watching. Have a great day.